Hello everyone, it's Mr. Appel again, and I'm going to continue where we left off last time. So you may recognize this figure. Looks like what we had before, although there's some extra stuff going on. Don't worry about that for the moment. So what we have is that triangle that's divided by a parallel line, and so we know that those side lengths are proportional. But I'm going to do something magical here. Watch what happens. I'm going to take one of the tops of that triangle and separate it so it's no longer a triangle. So now what we really have is three parallel lines. And those three parallel lines are cutting those two transversals in a certain way. Right? So you see 1, 2, 3 lines. I can highlight them for you. There's 1, there's 2, there's your 3 lines. And they're cutting that transversal and that transversal. And what we're interested in is, does the same ratio of the sides hold true like what we saw when it was a triangle? Right? When it was a triangle, we knew that this side and this side was in the same ratio as this side to this side. Those sides were divided proportionally. Well, the same thing is going to be true here. So when we have those three lines, they divide these two transversals proportionally. So let's get that formal definition down so you can kind of see it. So we say if three parallel lines intersect two transversals, they divide them proportionally. So that's all wordy and a little hard to explain, but basically all you need to know is if you've got three parallel lines, they cut the transversals in the same ratio. They cut them proportionally. So in this example, I know that the ratio of A to B is going to be the same as the ratio of C to D. So I can say that A over B has to be the same as C over D. And all those words aside, that's really what it means. So when you see three parallel lines, you know this must be true. Okay, let's look at another situation, a little different than the ones that we've seen already before. So here I've got a triangle, and I've got an angle bisector in that triangle. So in this case, I'm bisecting angle A. So ray AB here is bisecting that angle. Now, one thing I want to dispel, you might be looking at this and thinking, well, if it's an angle bisector, it must bisect the third side. It must bisect CD. And that is, in fact, not true. And I can show you really easily that that's not true. Okay, this figure's been set up to maintain that angle bisector. So you see these two angles are still the same. But I think you'd agree clearly CB and DB are not the same. So it does not divide that third side into equal parts. However, there is still an interesting relationship here, which is the ratio between BC and BD. So it cuts that third side in the same ratio as AC is to AD. Let me just try to show you what I mean by that. So if you just sort of follow AC for a second, if I take point C and I drag it and make AC longer, what happens to BC? Well, it also has to get longer, proportionally so. So if AC is really long, BC has to be really long. If AC gets shorter, then BC has to get shorter. And so that is the relationship when you have an angle bisector in a triangle. So again, the formal definition you should have in your notes, this is really the formal definition of that theorem. If a ray bisects an angle of a triangle, so if this is an angle bisector, those two angles are equal, then it divides the opposite side into segments proportional to the other two sides. Wow, that's a lot of words. But again, all it means is it splits. You could sort of think of it as that angle bisector splits the left half and the right half proportionally. So I could say, for example, that the ratio of A to X is the same as the ratio of B to Y. Those sides are in the same ratio. And that is all for now. Thanks.